Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video I'm going to go over hydrolysis in a single slide. The word hydrolysis means to break bonds with water. And typically we're going to be breaking carbon-nitrogen double and triple bonds, carbon-oxygen bonds where the oxygen is bonded to an R group, and carbon-carbon pi bonds. Now, normally carbon-nitrogen single bonds don't undergo hydrolysis, but in the case of an enamine, where you have a nitrogen single bonded to a carbon that's double bonded to another carbon, we do actually break both the carbon-nitrogen single bond and the carbon-carbon pi bond. For every bond broken on hydrolysis, a bond to oxygen will be created. Now, hydrolysis involves combining excess water with an acid catalyst, and sometimes a base catalyst can be used instead. These reactions are reversible with excess water favoring hydrolysis. It can be tricky to recognize when you have a hydrolysis reaction because the reactants that are put on the reactant arrow can be represented in many different ways, such as shown here. We can have H plus or H3O plus to represent a generic acid. We can also use H2SO4 or TSOH or any other specific acid that can be put on the line as well. A lot of the times they'll include both the acid and water. And as mentioned, sometimes we use OH- with water. Some hydrolysis reactions, like that of an alkyne or cyanohydrogen, require additional inputs. At the bottom of this slide, I have listed a number of hydrolysis reactions. And if you're looking at that and panicking, thinking, how am I supposed to keep track of this many reactions? Don't worry, there's a really easy trick to keep track of this. I call it the hydrolysis shortcut. The first thing we're going to do is locate any carbons that have double or triple bonds to nitrogen, a bond to an OR group, or a double or triple bond to another carbon, as well as the central atom to any enamine functional groups. Next, we're going to cleave all the carbon-nitrogen bonds and carbon-oxygen bonds that we've identified from step 1, and we're only going to cleave the carbon-carbon pi bonds. For however many bonds you cleaved from the carbon, add back that number of bonds to oxygen. In other words, if you cleave one bond, you're going to get a COH back. If you cleave 2 bonds, you'll get a C double bond O. And if you cleaved 3 bonds, you'll get back a carboxylic acid. For the non-carbon atom that you cleaved from the carbon, add back that number of hydrogens to it. And for alkenes and alkynes, the more substituted carbon will get the oxygen, and the least substituted side will get the hydrogens. Let's go through all of these examples. For all of these reactions, the first thing we're going to do before we draw the products is say which bonds we're going to cleave. In this first example, we have a carbon-carbon double bond, and we're only going to cleave the pi bond. So we're just going to cleave this pi bond right here. For the second, we have an alkyne, and once again, we are only going to cleave the pi bonds for the carbon-carbon. In the third example, we have a nitrile, and that is a carbon-nitrogen triple bond, and we're going to cleave all of those. In our fourth example, we have a carbon-nitrogen double bond, that's known as an imine, and once again, we cleave all of those. The next example, we have that carbon-nitrogen single bond, but the carbon that is single bonded to the nitrogen also has a carbon-carbon double bond. And in this case, that is the case where we cleave both the carbon-nitrogen single bond and the carbon-carbon pi bond. In the next example, we have a cyanohydrin, that is a carbon bonded to both an OH and a CN. And in this case, we do need to add heat for this hydrolysis reaction. But once again, we're just going to react by cleaving that carbon-nitrogen triple bond. On the other side, we have an ether, and that's an oxygen bonded to an R group on the right and on the left. So what we're going to end up doing is we're going to end up cleaving one of those sides. Next, we have an acetal, and there are 2 carbon-oxygen bonds. We're going to cleave both of those. And then last, we have an ester, and we have a carbon-oxygen bond as well. Once again, for however many bonds we cleaved from the carbon, we're going to add back that number of bonds to oxygen. So in our alkene example, we cleaved 1 bond, so we're adding in 1 bond back to oxygen. And as that note says, the more substituted carbon will get the oxygen, and the least substituted side will get the hydrogen. That's why we put the OH on that middle carbon. For the alkyne, we cleaved 2 pi bonds, so we're going to get back a double bond to oxygen, once again at the more substituted side. For the nitrile, we cleaved 3 bonds, so we're going to get back 3 bonds to oxygen. In the case of an acid catalyst, we're going to get the carboxylic acid, and in the case of the base catalyst, we're going to get the carboxylate anion. For the imine, we cleaved 2 bonds, so we're going to get back 2 bonds to oxygen. Same goes for the enamine. Notice the carbon that was bonded to the nitrogen and had the pi bond is where we're going to put the double bond O. For the cyanohydrin, it looks awfully similar to the nitrile, so we're going to get back 3 bonds to oxygen. For the ether, we're going to get back 1 bond, and of course we still have the other side, which will protonate. For the acetal, we're cleaving 2 OR bonds off, so that's going to give us a double bond O on that carbon as well. And lastly, on the ester, since we cleaved 1 bond, we'll get 1 bond back to oxygen. And once again, in the acid, we'll have the carboxylic acid, and in the base, we'll get the carboxylate anion. In most organic chemistry classes, we don't care about the group that we cleaved off for the most part, but in case you were wondering what happened, on the bottom left where we had the nitrile, that nitrogen that we cleaved off, we'll simply get an NH3. With the imine, we'll get an NH2R. For the enamine, we'll get an NHR2. And with that acetal on the right-hand side, we will get 2 equivalents of alcohol back. Same with the ester, we'll get 1 equivalent of alcohol, that ROH. That's pretty much it for hydrolysis. You can use that shortcut as long as you recognize the groups that it works on. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.